So hello everyone, this is lecture 30 for the electricity in magnetism. In the last lecture we have started the electromagnetic waves and we were seeing that how can we write the solution for the differential equations of the waves for the electric field and for the magnetic field. So today we will discuss that in electromagnetic waves the momentum and the energy is also associated with them. So how can we describe them and how can we write the expressions for them? So we'll see in this lecture that thing. So we know that E is represented in the free space in this way and B in this way, and we also find the speed is nothing but 1 upon epsilon naught and the mu naught and under root, and B naught was equal to E naught by C. So we have seen all these things. Now what is energy density stored in the field? So in a normal case we know in the electric field the energy stored is represented by this formula 1 upon 2 epsilon naught E square, and if it is in magnetic field then the energy stored is represented by 1 upon 2 B square by mu naught. So it is something like epsilon naught is analogy of 1 upon mu naught. So it is for the magnetic field, for the electric field. So this amount of energy is stored inside the fields. So this expression we will use to calculate the energy stored in these fields. So we represent the electric field energy will be by UE and this will be UB. So let's find. Now in the place of electric field we will write this expression, and in place of magnetic field we will write this expression. So U is equal to half epsilon naught E square. So E square will become E naught square and the cos square. So this will be your energy in the electric field. Now we need to find the average energy stored. So we need to find the average of this value. Now see, this is cos square theta. So cos square theta, average of cos square theta is nothing but 1 upon 2. So you can find the average of any function using this expression, that is 1 upon 2 pi 0 2 pi, and that will be your function and d theta. So this will give you average value. So you can solve it. It will give you 1 upon 2. For the sine square theta also it will give you 1 upon 2. And using the formula for, means if you calculate for the cos theta or sine theta, this will give you 0. So that's how you can find the average. So the average of this will be remain same, but average of cos square will be 1 upon 2. So the average value of UE will become 1 upon 4 epsilon naught E naught square. Now let's find for the average energy for the magnetic field. So in place of B we will write this expression, B naught cos theta. So the square will become, again it will give us the same value. In place of E naught square we will get B square, B naught square. So it will be mu B, means UB will be 1 upon 4 mu naught B naught square. So this will be average magnetic energy. And if you substitute here, means in place of B naught we know this expression, B naught equal to E naught by C. This will give you this value, and now mu naught C square will be equal to epsilon naught from here. 1 upon mu naught C square will give you epsilon naught from this relation. So in place of 1 upon mu naught C square we will write epsilon naught, and see this energy is same as was stored in the electric field. So these average energy will remain same. So if you need to now find the total energy, so that will be equal to sum of these, it will give you 1 upon 2 epsilon naught E naught square. So that's how we say that energy stored is totally in the electric field or the magnetic field, and that will remain same. So we can write either we can use this expression, or this expression will give us the same energy. Okay, so this is the average energy stored in the electromagnetic wave. So both are equal. Now what is energy flux density? We already described the Poynting vector, so that represents the energy flux density. So it is equal to E cross B and the mu naught. So let's find this. Now E is given by E naught cos theta, and B is given by this B naught and cos theta. So we just take the cross product. So it will give you this E naught B naught cos square kz minus omega t plus delta. Now see, this Poynting vector is nothing but power per unit area, means energy per unit second, means energy per unit time, and the per unit area will give you your Poynting vector. So this is nothing but energy per unit time will give you power, and power per unit area, this is nothing but intensity. So this will be equal to, now average value of this will be, means again here we have cos square theta, this will give you 1 upon 2. So average value will become 1 upon 2 mu naught E naught and B naught by C. So small correction, here we just substituted B naught by the E naught by C, as we already seen this expression. So now this will be B naught equal to E naught by C, and this is E naught. So this will become E naught square, and it will be mu naught C. Now multiply by C and divide by C. So it will become mu naught C square and C above. So mu naught C square will give you this expression, 1 upon mu naught C square equal to epsilon naught. And there will be 1 C above, so it will give you 1 upon 2 C epsilon naught E naught square. So this is your intensity. And you can see this, take this C outside, it will give you 1 upon 2 epsilon naught E naught square, and that is nothing but average energy. So the I intensity is nothing but average energy multiplied by C. So this expression you must remember, very important expression this is for the electromagnetic waves. Now if energy is associated with the EM waves, then momentum is also associated with the EM waves, we know that. So we just describe now we will describe the momentum density that is stored in the field, and we represent that by PD. So let's see, EM wave not only carry energy but it also carry momentum, and that is represented by momentum density, that is PD. So momentum density is stored in the field is given by, so this is the expression you must remember for the momentum density, that is Poynting vector divided by c square, and this is your momentum density. Now find the average value of momentum density, will be average of this divided by c square. So average of Poynting vector we already find, that will be equal to this energy multiplied by c, because this is intensity and that represents the Poynting vector, so it will be average energy and c. So this will be equal to, in place of this, write the average energy multiplied by c, and in the denominator you have the c square, it will give you average energy divided by c. So this is your momentum density, means the momentum per unit volume applied on the any surface. So if the momentum is applying, now there will be change in momentum and there will be some force applied, and if there is force, then there will be some pressure applied. So this EM wave will apply some pressure on objects, and we call that as radiation pressure. So let's see what is the radiation pressure. So we will see on the different surfaces. First we will say that this object will absorb all the EM wave, complete EM wave it will observe, means absorb. Then what will the pressure applied, radiation pressure what will be. So let's say that wave is coming and it will be absorbed up to the c delta t length, it will be absorbed up to this length, and up to this length the momentum will become 0. So the change in momentum will give you force, and you can find the pressure after that. So let's see, we know what is momentum density, it is momentum per unit volume. So volume will be given by, if this is your cross section area, so AC delta t will give you volume. So PD, that is momentum density, multiply AC delta t will give you momentum applied. So change in momentum in time delta t is given by, will be this average, means momentum density, and AC delta t. So average momentum density we just find it, that is equal to average energy divided by c. So average energy c multiply AC delta t, and pressure is nothing but force per unit area, and force is rate of change of momentum. So del p by del t, in place of del p we will substitute this, in place of PD we will write this energy divided by c. So we will get this expression. Now A delta t will cancel out and c will cancel out, and you will get this is equal to average energy, only this will remaining, and this is nothing but I by c. You can see from here this intensity will came out to be average energy multiplied by c. So from here this average energy equal to I by c. So pressure can be given in the terms of intensity. So if you know that what is the intensity of your wave, then you can just find the pressure also. So the radiation pressure is proportional to the intensity. So the large is the intensity and the more will be the pressure applied. So you must remember this relation, the pressure equal to I by c. Now this is for the surface when the wave is completely absorbed. But if the wave is not completely absorbed, it is reflecting, means it is completely reflecting surface, perfectly reflecting surface, no wave absorbed, then change in momentum will be double, means it will be, means it is mv this way and minus mv, it will give you 2m del v. So that's how you will get 2 multiply here. So change in momentum will be double of this. So if it is double of this, then pressure will be also doubled. So in the expression you will get 2I by c. And here also you can see that pressure is I by c in the positive direction, then it is minus I by c. So change in pressure, and that is equal to giving you the pressure applied on this surface, that will be equal to I by c minus I by c will give you 2I by c. So pressure will be doubled in that kind of surface. But now there is third case, that reflecting wave is 0.8 I by c, means it is coming 100%, now it is backing 80% and 20% is absorbed. So what will be the pressure then? So again this minus this, so it will give you sum of this, it will give you 1.8 I by c. So that's how you can calculate for the different kind of surfaces that how much radiation pressure will be applied. So you must remember this thing. Now if it is completely reflecting or fully reflecting, but it is incident on the oblique angle, okay, means some at theta angle. So what will be the pressure then? So again we need to take the x direction component only. So it will be I by c cos theta, means if I by c is coming, so it will be I by c cos theta in the plus x direction and minus I by c cos theta in the negative direction. So total pressure will be this minus this, it will give you 2I by c cos theta. So this will be your radiation pressure if it is incident obliquely. Okay, so that's it. Let's see now the new thing. Now we'll see EM waves inside the matter, means here we studied EM waves inside the vacuum or the free space. Now we'll see that if the EM wave is traveling inside a dielectric medium, or it can be a magnetic medium, then how our equation will be changed. So let's see. So we already described the 4 Maxwell's equations inside the matter, so we'll use them. So we will apply them only on the linear homogeneous dielectrics. So what is the condition here? that epsilon is nothing but epsilon naught epsilon r. So this will be introduced now because it is different for different mediums. And mu is equal to mu naught mu r, where this epsilon r is nothing but dielectric constant, and this is relative permittivity. So permeability. So and d is, this is displacement vector equal to epsilon naught e plus p, and here p is polarization, and this is written as epsilon e. And as same, h field is written as b by mu naught minus m, and b is equal to mu h. So you must remember these expressions, we will use them. So Maxwell's equation will be del dot d equal to 0, because there is no free charge inside the medium and there is no free current. So del dot d will be 0, and you can write d, in place of d it will be epsilon e, so it will give you divergence of E is also 0. And second equation, del dot b is 0 and del cross E is minus del v by del t. And fourth equation for the matter was del cross h equal to del d by del t, and in place of d you can write again epsilon e, so it will give you del cross b, and in place of h you can write mu h. So it will give you, means h is equal to b by mu, so in place of h you will write b by mu, so mu will go into the right side, so you will get del cross b equal to mu epsilon del e by del t. So these are your 4 equations, Maxwell's equation for the EM waves inside the matter. Now we will use them to find the wave equation now. So again we will just take the curl of this, we will apply the same way as we did in the free space, and we will find the expression. So we will get these two equations, del cross E equal to mu epsilon del square E by del t square, and del square B equal to mu epsilon del square B by del t square. Now see what is the difference here from the previous state. Here we have the mu and epsilon, not mu naught and epsilon naught, because now we are in the medium, so just these will be changed to mu and epsilon in place of mu naught and epsilon naught, and everything will remain same. And the speed, there was speed of light, but here you will get some arbitrary speed, that is v, and that will be given by 1 upon mu epsilon. And now we can write mu as mu naught mu r and epsilon as epsilon naught epsilon r. Now this 1 upon mu naught epsilon naught will be taken out, will be given as c, that will be c, and remaining terms will be mu r epsilon r. So this will give you your refractive index of the medium, so that will be represented by n, and n is refractive index of the medium, so c by n. So speed is nothing but c by n. So we use this expression in the optics very much, so you must see that how we get this expression. So this is how we get this. So n is your refractive index. Now if you need to find the n for any medium, just write the mu r and epsilon r, you will get the n. And if let's say that the material is not magnetic, means it is non-magnetic, then the mu r will be 1, then simply refractive index will be epsilon r. If mu r equal to 1, then the material will be non-magnetic medium, so this refractive index will be given by under root epsilon r simply. Now we know speed is given by omega by k also, and speed we find just, so it was c by n, so speed can be given as c by n also, so it is equal to omega by k. So we can use this relation also somewhere, means there can be question asked based on this, so you can solve them if you know the relation. Now what change come, in place of mu naught we have mu here, and epsilon naught we have epsilon, and in place of c we have v here. Now energy also, in place of epsilon naught and the mu naught, we will have in the total energy will be 1 upon 2 epsilon e square plus b square by 2 mu, and the Poynting vector will be again 1 upon mu e cross b in place of mu naught. So only these things will change, others will remain same. And momentum density will be given by s by v square, in place of c square we have v square. So you must remember how the Maxwell's equation and how the wave equation will change in the matter. So this is the way they will change. Let's see one example based on this. The electric field E of an EM wave in dielectric medium is given by this. So electric field is given x y z t E naught x cap plus under root 2 a z cap exponential I k naught minus ct plus x plus under root 3 z. So E naught a k naught are constant, and c is given as speed of light in free space. We need to find the dielectric constant and constant a. So we need to find the dielectric constant epsilon r, and we need to find this a value, and we need to consider that it is non-magnetic medium, so we need to consider mu r as 1. So let's see. So we know in the exponential term how the equation can be written as, so exponential k dot r minus omega t, we saw this expression. Now we will compare this to find the k vector, or the means k is nothing but means propagation vector. So let's see the exponential term. It is nothing but I k naught, means just multiply I k naught inside, you will get k naught minus ct. So we will compare this with the omega t, and we will compare this second one, the k naught x plus under root 3 z with the k dot r. So r will be nothing but x cap plus z cap, and the remaining one will be x cap plus root 3 z cap and k naught. That will give you your k vector. So from the comparing we will get k equal to k naught x cap plus root 3 z, and the r will be here x cap plus z cap. When you multiply the k dot r, you will get the same expression k naught x plus root 3z. So that's how we have just find it k vector from here. And you can compare omega t with the k naught ct. So from here you will get omega equal to k naught c. So now we have the k vector, means the propagation vector, and we have the omega. So we can find the speed now. V equal to omega by k, and k is nothing but magnitude of k. This will give you k naught, and the magnitude this will be 1 plus root 3 square will give you 3. So it will be 4, will give you 2 here. So k naught will cancel out, it will be c by 2, and v equal to c by 2, and v is nothing but c by n. So equal to c by n, from c will cancel out, and n will, you will get n as 2. So n is nothing but refractive index, and it is given by under root epsilon r for the non-magnetic medium. So from here you can find the dielectric constant also, that will equal to 4. So you have refractive index, you have the dielectric constant. So that was it. Now there is one more thing they asked. They asked that find this A. So see this, in this expression, this is nothing but polarization vector. So it is in the last you can write n cap. So this is your n cap. Now k vector multiplied means k dot n cap must be 0 because they both are perpendicular. So that's how we can find the A also. So we already find this k vector, and n cap is given. So just dot product of this will give you 0. So do the dot product. So n cap is this, k dot n cap will be 0. So dot product will give you 0. Here from here you can find A equal to minus 1 upon under root 6. So this will be your answer. Now there is one more case. EM waves inside the matter, and this time the matter is conductor, means not dielectric. This time we have a conductor, and we need to find the wave equations for that. And this time a new factor will be introduced, that is conductivity, because if you place any free charge inside a conductor, that will flow to the surface. So we will understand that how it will flow, means there will be time, means when you just place some free charge inside the conductor, that will take time to reach the surface. That time is called the characteristic time, and for an ideal conductor that time is very instantly, means there will be no time gap, means to get to the surface. But for a normal conductor there will be some time, and we call that as characteristic time. So let's consider that Jf is nothing but current density, so that is equal to sigma E, that is for the conductor, we know this expression. And at t equal to 0 we place some charge, that is rho f, free charge. At t equal to 0 we place some charge inside the conductor, and we need to find the time, that what it will take to reach the surface. So that's how we can define. So for the conductor, your Maxwell's equation will be this: del dot D equal to rho f, because there is some free charge we applied, and del dot E will be equal to rho f by epsilon, and del dot B equal to 0, del cross E equal to minus del V by del D, so they will remain same. Now fourth equation is del cross H equal to Jf plus del D by del D. So from here, now see, in place of Jf you can write sigma E, and in place of H you can use the expression we previously defined, that equal to B by mu naught. So it will be B by mu. So this will change to del cross B, and here you will get mu multiplied to whole this factor, so it will be mu sigma E. In place of D you can write epsilon E, so it will be mu epsilon del E by del D. So these are your four equations for the conductor. And we know the continuity equation, del dot J, we already derived this. So del dot Jf is equal to minus del rho f divided by del D. This is your free charge density. So in place of Jf, just substitute sigma E. So sigma, it will give you divergence E equal to minus del rho f by del D. So we need to solve this equation to find the time. So just take this del rho, means this del dot E is nothing but rho f by epsilon. So just write it, rho f by epsilon. So from here del rho f by del T will be equal to minus sigma rho f by epsilon. Now from here take this rho f with the del rho f and del T this side and integrate. So we'll integrate from the 0, means when we initially place some charge, up to the some time t. So here we'll integrate from the 0 to t. So this will give you rho f t equal to rho f naught. When you solve this you will get some log terms, and log will give you exponential term. So rho f t will be equal to rho f naught exponential minus sigma by epsilon t. Now this epsilon divided by sigma will give you your characteristic time. So it will be rho f naught exponential minus t by tau. So tau is nothing but epsilon divided by sigma. So this will give you your characteristic time. And what is this characteristic time? It will the time required to move the charge to the surface inside a conductor. Now see, if the conductivity, means it is an ideal conductor, the conductivity will be infinity. So this time will be 0, means it will reach instantaneously to the surface. But if it is not a ideal conductor, then it will take some time because it is a normal conductor. And the ideal insulator, what happens? In the ideal insulators, the conductivity is 0, no conductivity in the insulator. So it will be, this tau will be tends to infinity, means it will take infinite time to reach to the surface. So that's what happens inside a insulator. So that's how you can just find, means identify the ideal conductor or ideal insulator using the help of characteristic time. So this is the case. And also we can describe good conductor and the bad conductor in terms of this. Means 1 upon omega will give you the time dimensions. So this tau must be less than equal to 1 upon omega for the good conductor. And from here you can just write tau is equal to epsilon by sigma and less than equal to 1 upon omega. From here you can write sigma will be greater than equal to epsilon omega. So this is the case for good conductor. And for the poor conductor, this tau must be very greater than 1 upon omega. This 1 upon omega is nothing but time. So it will give you dimension of time. So it must be very greater than this 1 upon omega. Then you will say that it is poor conductor. And sigma must be less than equal to omega epsilon. So that's also you can describe means poor conductor and the bad conductor. So you must remember these things. Now let's see that how can we use them to find the equation of waves for the electric and the magnetic field or the EM waves inside a conductor. Now see, if you place some charge, means it is a good conductor, and you place some charge inside the conductor, then that will reach immediately to the surface. So this will be give you free charge density inside 0, and this will also give you 0. So del dot E will become 0. So now we will use this equation to find the wave equation. So again we will take the curl of this, and it will be del cross B, and we will substitute del cross B from here inside this. So we'll get this expression. So expression will be del cross A equal to minus del by del T del cross B. So we just substitute the value of del cross B, and del dot E is 0. So from here we will get this expression. So we just substituted it here from here. We'll use this. Now del cross E equal to this expression. Now this is the equation for the electric field, means electric wave or the EM waves inside the conductor. And similarly you can derive for the B also. So this is your wave equation. Now see, here is what is the difference from the dielectric medium. Here you have this one extra term, this sigma. So this represents that if there is conductivity, then there will be this kind of equation will be framed. And if you just turn to the dielectric medium, then there will be no conductivity. This will become 0. So this will be neglected, and you will get only this term. So that's how you can just get the term means you can get dielectric back. So from the conducting medium. So you must remember these are the equation for the electric and the magnetic field inside a conductor. Now this is a differential form. So we need to find the solution for the E and B. So that will be also different because there is some extra term. So in the next lecture we will see that how can we write the solution for these equations in the terms of E and B, and how the wave will be different from the previous case. So that we'll discuss in the next lecture. So thank you everyone.